Hello there guys, welcome back to another maths video, and in this one it's Halloween. We have got a very spooky looking integral. Actually, it's a completely normal looking integral, but let's just do it anyway. So what we're going to do to start with on this one is we're going to notice the denominator. It's of course cos x plus root 3 sine x, and then it's also being squared there, but we'll worry about that later. What I'd like to do preferably is not expand all of that out because it would be a bit messy. Rather, I'd like to write this as one trig function, and we know that we can do that using the harmonic addition theorem. Can I write this as like r, and then maybe either a sine or a cos of x plus or minus maybe some angle? And it turns out, yes, we can. So there's a typical way of doing this. This question's pretty nice though, because what you can do here is you can factor a 2 out, and then you can rewrite the inside like this. And the reason why this is nice is because the numbers that you get, 1/2 and root 3 over 2, are already nice values that you get from particular trig functions. So one way to do this is to realize that cos of, and then this is in radians, so pi over 3 is 1/2, and sine of pi over 3 is root 3 over 2. So I can actually replace the number 1/2 and root 3 over 2 with those things there. So I can rewrite this as cos of pi over 3 times cos x plus sine of pi over 3 times sine x, like that. And now I can notice that this is actually just the compound angle formula or the addition formula for cos of pi over 3 minus x. Okay, and then that's going to be my new denominator, and that is super nice. So I can rewrite my integral as follows. I can write it as the integral from 0 to pi over 3 of 1 over 2 cos pi over 3 minus x, and all of that is being squared dx. And now this is super nice because we can actually square it now, and we're going to basically get something with a sec squared in it. So we're going to get the integral from 0 to pi over 3 of 1 over 4 times cos squared of pi over 3 minus x dx. And this can be rewritten as a quarter times the integral from 0 to pi over 3 of sec squared of pi over 3 minus x dx. Now we want to integrate this thing. Now it's lucky because sec squared has a very nice integral. And by the way guys, one thing that I'm going to do to make my life slightly easier is I'm going to rewrite this as a quarter integral from 0 to pi over 3. And instead of sec squared of pi over 3 minus x, I'm going to rewrite this as sec squared of x minus pi over 3. And you are allowed to do that because I've basically just timed the inside of that by the number -1. But you can do that because you can do that in cos, right? So cos of theta is the same as cos of minus theta. And of course, when you square it, that doesn't make a difference. And when you take the reciprocal of it, that's the sec squared function. It doesn't matter. So I'm allowed to do this. The reason I'm doing this is because it makes the integral slightly easier to think about the chain rule and stuff. So I'm going to have a quarter. The integral of sec squared is tan. And remember, I've got to use the reverse chain rule here, but the derivative of the inside is now just the number 1. So nothing too interesting happens. And I just end up getting tan of x minus pi over 3 from 0 to pi over 3 like that. And then I can just keep going through. So I've got tan of basically 0 here because it's pi over 3 minus pi over 3 minus tan of minus pi over 3. And then this is just going to be 1/4. And then, of course, tan of minus theta is the same thing as minus tan theta. So basically minus tan of minus pi over 3 is the same thing as tan of pi over 3. And most people will know, but tan of pi over 3 is the number root 3. So this is a quarter root 3, or root 3 over 4. And that's the answer. That's the answer to the integral. Root 3 over 4. Now, one thing I want to go back and mention is some people might say, technically, there's another way of doing your compound angle formula here, because instead of saying, oh, well, I'm noticing that cos of pi over 3 is 1/2 and sine of pi over 3 is root 3 over 2, you could also say, well, hold on a second. I'm noticing that sine of pi over 6 is 1/2, and cos of pi over 6 is root 3 over 2. So why not do it this way? And then you could end up rewriting this as 2, and then you'd have a sine function and you'd have stuff here. Why don't you do that instead? And the answer is you can, but it's just a little bit more annoying. And that's because 1 over sine squared, that's the integral of cosec squared, it's less commonly remembered off the top of the head. So it's much easier to do the integral of sec squared than the integral of cosec squared, in my opinion. But it's not a problem, you can do it that way. And also the slightly unconventional way that I've done the harmonic addition theorem, you can just do it the normal way. But this was like a slightly faster way of doing it if you spot that pattern. Anyways, guys, that integral is equal to the square root of 3 over 4. Happy Halloween. See you in the next one.